signal will see only bitumen, but as I wait, other things will happen. So at time 0, indeed, we had only the red, which was the P3, the bitumen, and I knew already, because we did separately, what would the rejuvenator look like. That would be the green. But now I wait, and I don't know if you can see, but I was looking for this peak and that peak over here. And if you look in this picture, you start seeing the rejuvenator gradually developing little by little until it reaches the peak that it should be when that particular substance makes it to the other end. And the same happens here. It starts, it's hard to see probably from where you are, but as the time was increasing, these curves were developing until eventually we got the same peak as we had. What did this mean? It meant that now I also had a technique that allowed me to tell exactly which component from the rejuvenator was going how fast where. So if ideally I wanted, as a chemical engineer, as a chemist, to choose a rejuvenator whose components will go as fast as possible. And that's what this allows you to do. It allows you to really have a multi-diffusion model for each. Yeah, this is nice picture. Actually, I forgot I had it. It's also in a little better discretization, the gradual increase of a particular component. And then, by using this, I can also compute the diffusion times, which is also what the chemist wants. Okay. Why do we do all this? Because at the end of the day, we want to rejuvenate the bitumen. We want to push this curve to that curve. And how do we do it? We brought in another liquid or another emulsion, whatever, another component. Think of liquid to make it simple for those who are not liquid. For those of you who are familiar with complex moduli and frequencies and this and that, we'll tell immediately that the rejuvenator for this particular case is a liquid, for the mere fact that it doesn't plot nicely in this plot. Okay, now we know it's a liquid. We knew it because we put it in, but it's nice to prove the theory right. Now, if you look at a given temperature, then it becomes more interesting, because what I'm showing here is the original H bitumen, the rejuvenator in terms of its own stiffness, and what happened when we mixed them. Both ways, and theoretically and via the measurement. So you have a stiff material, and you try to reduce its stiffness by putting something soft and mixing it. And that's what it is. That's the type of techniques that we'll speak about in this lecture. There are other ways to rejuvenate. We'll do it next time. Some more technicalities. From the theory of mixing, if you have two materials that you try to mix and to find their frequency response, what will happen? How does the new material behave now? What's important is this mixing factor here, which really determines how efficient the two materials interact or not. And what you'll see is that I plotted for all the rejuvenators that I had for this lecture, I plotted this coefficient here for their mixing with three different H bitumens. And you see that when this interaction coefficient was high, that's when we got the largest reduction in stiffness. It's an indication, if you wish, if this comes high, it shows that you're mixing the two liquids, the two substances go in the right direction of mixing. Why the right direction of mixing? Because what is the right direction of mixing here? The reduced stiffness. Huh? Also, it was interesting that very soft rejuvenator, the red lines here show the stiffness of the rejuvenator. Very soft rejuvenators interacted best with the bitumen, and, we'll see it later, resulted to the highest reduction. Stiff ones did not. Look how stiff this was, and look how little its interaction was. And when we look at the stiffness plots, you recognize that this was not a good choice. This is a summary of the features of the rejuvenators in terms of this attempt to split them in groups, in particular chemical groups. The bottom here are the bitumens we use, the 8 bitumens, and you notice that they are rich in what is known as asphaltenes. Asphaltenes are a type of molecules in bitumen, a type of molecules which happen to be stiff and large. And you notice that the industry is developing rejuvenators where their asphaltenes are small percentages of the total. Why? Because that guarantees a soft material. If you have too many of these are large molecules, they create a stiff material. The reason there are many here is because these are oxidized. These were not virgin bitumens, unaged bitumens. It's the oxidation that raised the percentage of this particular chemical component. And the hope is that now we're going to add a component with lower percentages of this one, the rejuvenator, in the hope that because of the mixing theory, the average result will drop. And that's what it is about. In terms of numbers, you will find this concept of the asphaltene index as an indication of how many of these stiff components one has in their mix. These are the rejuvenators that we can use from A1 to D. Forget this for now, we'll get back to those. And you see that their asphaltene index is quite low in comparison to the H bitumens index. They have softer components. Why are they softer? Because the complex modulus says they are softer. You see, the complex modulus of those is lower than the complex modulus of the H bitumens. And a chemical indication that the chemistry can control is to say, okay, then I'm going to choose rejuvenators with low asphaltene index because I know that they will have low complex modulus. We had two exceptions where a substance had a high asphaltene index but a low complex CR modulus. And I'll get back to them later today. This is a summary of stiffnesses really, asphaltene indexes. You see the bitumens with very high asphaltene content, but these ones, they keep going up. The rejuvenators with low contents, and the mixing somewhere in the middle. And the question is how much? how much rejuvenator do I need to get me where I want to go at minimum cost. This more or less shows the same. It shows that starting with the blue lines, which is, say, the asphaltene's content of a given bitumen. This is the asphaltene's content of the rejuvenator, sorry. When you put them together, you got a green line. And it happens the same for all the components. By choosing the chemistry, you try to lower or to increase the percentage and its effect on the mechanical properties. And as you would expect, the more you put, the better it gets. The more you go towards the desired mechanical response, the more or the less you drop the number of large molecules that you have into your mix. And as we saw, this will imply also better mechanical performance. The GPS is a particular technique which allows you to more or less gauge the distribution of molecular sizes into your material. And you notice that the blue one here is a particular age bitumen, and as you go down, the drop really reflected in the different amounts of aging that we can impose on this material. The less age, the fewer large molecules. When we mixed it, this was our rejuvenator distribution, not very large molecules in this area. The green was the distribution of the H bitumen with large molecules. For the particular combination, the purple line is the reduction. You see, this area dropped, but also the whole curve has moved in that direction, which is the direction of the small molecules. And the same for others. We also looked under the AFM. AFM is really a sophisticated microscope that allows you to look at very small dimensions. This is 10 micrometers. We saw this picture before. So we looked at the bitumen before aging, and we looked at the bitumen after aging. And as we expected, you see two different universes. Things went missing after the rejuvenation, the aging. But depending on the type of rejuvenator, starting from this end, for some particular rejuvenator, after its application, we managed to restore the structure back to more or less the same as the original. For other types of rejuvenators, we got some very different looking pictures. Look at this. And magnification, comparing the two, is here. This is one particular type which produced a good restoration and corresponding mechanical properties. This is another rejuvenator, but look at the difference. It was nothing like the original. Going further in, for that particular material, it's like if it created a whole new face of material surrounding some of the original structures, the structures before rejuvenation. This is a magnification of the magnification, and it looks like Mikado, for those of you who know for a particular type. Remember I said I speak about this particular rejuvenators later. These were the rejuvenators that created these pictures. And when we speak to the industry, indeed it's a particular origin of material which creates this. Assuming that you rejuvenated something, time will still pass. It means that starting from the original, the age, we drove it down because of rejuvenation to the desired level. That's what we spoke before. but because oxygen is still there, because ultraviolet is still there, it will increase. And that's a test, test results, how after some aging process, indeed, it started going back to the aged structure. And if you follow the same analysis that I present until now, you can literally see now time going forward. Because now it was aging again. And yes, it makes a difference, excuse me, from product to product. And that gives them also a market advantage. The product may be more expensive, but it doesn't allow aging to occur at the same rate. We also went out in the field, first very carefully, and asking permission to use material from limited lengths of a highway. Naturally, the road authorities are very apprehensive of us. But when it worked, when we could show that by applying the techniques that I discussed earlier, and when we showed them the results that, look, it does mix, and I have a proof at laboratory level that it does mix, they have allowed us since to use longer stretches, sometimes in the same location, to get us really more data. And we're still discussing in-service rejuvenation. Does it improve the mechanical properties? We saw that it does. Once we apply it, is it dangerous? If it takes forever to be absorbed, it will be slippery forever. It wasn't. It takes about an hour and a half to mix some products. And yes, considering that it restores the properties, nice. Part of what we did was also field studies. I won't spend too much time on it. We did a classical field study test to make sure that the skid resistance was not affected, the sound absorption was not affected, texture, permeability. You don't want to create a mix where now it becomes impermeable. I won't insist on that. Overall, our experience has been positive. As I said, we had a 3 years first cycle, and now we're into the second cycle for field rejuvenation. And to close it, very briefly, some issues for the service, end of service rejuvenation. What we said, this is what happens when, for some reason, you are convinced that your pavement has to be removed. Now you have a pile of black rock. If you do it properly, we won't go into this. You want to make a new mix out of it. And one way to do it is to bring in the rejuvenator. We do use a lot of recycled asphalt in Netherlands, primarily because we don't have any raw materials other than milk, flowers, and dust, and sun. So the idea of using the raw material in a structured way is very appealing. There are some limitations, and I wanted to put them up. Our industry at the moment feels very comfortable in using recycled material without any particular need for rejuvenation, up to these percentages for the lower layers, if you wish. When you go to wearing courses, the previous experience showed that perhaps it wasn't such a wise choice. You had to do something rather than just put it there. And for the same reason, in porous asphalt and SMAs, where you want good stone-to-stone contacts, you are reluctant to use a stone whose origin perhaps is dubious. And the quest for us is to convince our authorities that this can be done if we do it properly. Just an example, we played with changing the percentage of rejuvenator from 50 to 65%. So we see stiffness here in red and blue for one mix that we had 50% not rejuvenator, recycled material. This is the red line here. And then just a 15% difference between those two, if you look at it in terms of stiffness change, is way out of proportion. The rule of thumb in Netherlands at least is that up to about the 65%, probably you can live with these high stiffnesses. Above that, you need rejuvenator. You need to bring the material back where it was or midway there. Very briefly, what are the issues with the end of service rejuvenation? You have to do it in a plant. You have, I chose pictures from another concept, but imagine that you are seeing the drum in here, and the blue material is the aged material, and somehow the yellow is the new material that you expect to mix. And again, it's an abstraction, but it will serve for our needs. You want the yellow to mix with the blue to what? All it will do is it will physically put two different materials together. Huh? If you wait long enough, if you keep rotating, what will happen is the distribution of the yellow and the blue will start changing. You get some lighter blues on their way to being reds. I chose to show by red the better physical distribution of the two materials now. Huh? And eventually, if you keep steering, hopefully you will get something that looks like this. Now you have a good geographic distribution of the two components. Microscopically, what you have done, what these red dots mean, is that you started with the aggregate. I chose to paint it black, which was coated with something from its previous life. The light green here, or the green, is the coating of the aggregate as it came from the road. But now, the external coating is the rejuvenator, is the new material. But that's not enough. Huh? It's necessary, but nothing has happened. All that's happened is the plant has to produce a good distribution of the rejuvenating material. But in reality, you need time for diffusion to occur, as it occurred in the lab, for these two gray scales to become one, to become this one. And that brings us exactly back to where we started, which was looking at how, at lab level, the two mix together. But without both the physical process of taking the rejuvenator where it should go, and there are several plant facilities that can do that, and the physical process of diffusion, you cannot do it. To close it, we have been involved for the last 2 years in an attempt to somehow create a system that looks at individual components, the environmental issues that affect the material on the pavement, and environmental issues can also bring temperature. Huh? These materials tend to oxidize more in hot environment. When oxygen gets in there, it makes a reaction. That's why it changes your bitumen to something else. We can bring this in, and we have to bring it in because it also makes a difference depending on the bitumen type. And then gradually start bringing in the mechanical aging, but also the effects of the rejuvenation. That's what we discussed today. Hoping to create a cycle that addresses the whole life time of the material. In a very similar fashion to what you guys have here, we have set up what we call InfraQuest. It's really we don't call it a center of excellence, we call it competence. Being in a Dutch environment, you learn to be circumspect. The idea is that somehow we work with the state to address their needs, think in the way that you operate in your structure here, and interact also with the industry, a large sector of the industry, which provides provides the material, which provides all we need to do our research. I'd like to thank you on this. Hope that at some point we will have the chance to see you in Netherlands. This time of year it is a magic place. We hope that somehow we have the chance to see you at the right time in the right place. Thank you.
All right, we'll take some questions. Tom, thanks, Tom.
How temperature dependent is this diffusion process? Like in the lab it was I think 130 Celsius or something, but what do we do in the field? I mean,
think of it, diffusion is a molecular process. Molecules, if you heat them up, they jump. So as you increase the temperature, diffusion goes faster. It's a molecular process. The molecules like to jump.
So that heat blower that you showed, that's probably
no, not a heat blower, it was an air blower. What they went to Russia and they bought a jet engine, which they mounted on a truck, just to blow air to drive the material further in. And that's what it is. To make sure that you don't just have a surface solution, but something that takes, because oxygen, in Netherlands they use a lot of very open mixes, which means that air has the capability to go way further in than would normally go in a standard dense mix. So it's not enough to just do a few millimeters on the top, you want to get it inside, otherwise it's going to come out. Yes.
Okay.
Please don't fight.
All right.
That was a great presentation.
Thank
I
you.
have two short questions. First one is, what is the typical dwell time for the rejuvenator for the material after you use the whole pavement? How long is that for the rejuvenator?
The diffusion results that I showed for some of the products show less than 90 minutes. Fuel diffusion. The strive of the industry at the moment is to even reduce that. But, yeah. The Dutch, remember I showed the application process of 9. By next day, the road is open. And for some products, if they take longer, they spray some sand just to make sure that the friction for 1 or 2 days. One of the comments I had that it takes about 1 day to be careful of friction. But that's it. So literally, next day, if you do it on a Friday night or a Saturday night, by Monday nobody knew we're there, except that it's blacker now. Second.
And I was wondering if you looked at the mechanical cracking performance or locking performance, or the effect of rejuvenator on locking performance.
If you look at the very open mix, the main mechanical problem that you have, the first problem that you will see will not be racking and will not be cracking. I don't think it's cracked already. I mean, it's 40% void. It's already cracked. You don't have to crack it. Racking, think of an SMA. The reason people made SMAs, the reason the Germans made SMAs, was because the stone-to-stone contact gives you a very stiff mix. It doesn't rack very easily. If you come to Netherlands, you will never see racking. What it does do is it loses aggregate one by one. You can literally count them day by day and one is missing. So raveling, for our problem, is the main cause. But think of it, let's say that now you use it to make a standard mix. When you designed your mix originally, you already designed it to take into account both the cracking and the racking. The PG, more or less, gives you those limits. What you're doing here is to bring the PG where it should be, really. Coming from Netherlands, we don't think in terms of PG, or they don't, but that's what it is. You are readjusting your material to go where it should go.